It is time to talk about that very particular example of permanent dipole-dipole intermolecular force, the hydrogen bond. So let's dive straight in. The hydrogen bond, a particularly strong kind of permanent dipole-dipole interaction, and it forms between the slightly positive hydrogen of one molecule and a lone pair of an electronegative neighboring molecule. Let's look at an example. If we had water molecules and ammonia molecules together, like the diagram on the left, what we might find is the slightly positive hydrogen on the water would naturally be attracted to the slightly negative nitrogen on the ammonia. In between the two would form a hydrogen bond. Now, if this was very energetic, these two would be constantly just moving around and moving all over the place. It would have enough energy to escape the attraction of that interaction. But as we removed energy, as we cooled it down, what we would start to see is that the nitrogens would become fixed in position relative to those hydrogens, and we'd see the start of the formation of a solid. And this is very true with water. You see, water has that negative oxygen and those positive hydrogens. What we will find as we remove energy and the liquid water starts to freeze is the hydrogens will align with a neighboring oxygen. And though this diagram here shows another single water molecule lining up with the oxygen, actually what you're going to get is you're going to get a pair of water molecules. This doesn't perhaps represent the 3D-ness of it. But both lone pairs of the oxygen are independently going to attract the attention of a neighboring hydrogen. And so it creates this 3D structure where the oxygen has attracted the attention of two neighboring water molecules. It creates a hexagon, and this hexagon we shall now explore. The presence of the hydrogen bond creates these strong intermolecular forces which lead to certain physical properties, including higher boiling and melting points, high solubility in water, increased surface tension, and lower density in their solid form. And we'll talk about that as a particular example. Other anomalous properties as well, such as thermal properties and issues to do with the viscosity. All of these are controlled by the fact that there are hydrogen bonds in this substance. It's really hard to see in these diagrams because of their three-dimensional shape. But every single one of these red oxygen atoms has formed a hydrogen bond with two hydrogens. If you look at the one at the very top, on the type that are in the hexagon that's really clear and obvious, the one at the very top, you can see it's got its own two hydrogen atoms at the top, but it's formed those two purple lines to adjacent water molecules. So trust me, it really does. Each water molecule forms a hydrogen bond from its oxygen to two adjacent water molecules. And its own hydrogens will themselves form hydrogen bonds to adjacent oxygens on two adjacent water molecules. Every water molecule is attached via a hydrogen bond to four other water molecules. Forms this hexagonal shape with an interior angle here of, well, the interior angle of a hexagon is 120 degrees. These interior angles are 109.5. It's not a flat hexagon. It's a kind of like corrugated hexagon. It doesn't sit flat because of these particular bond angles. What actually happens is it kind of forms like almost a tetrahedral-like shape when we have these four bonds in place. And so it has the same interior angle as the tetrahedron when we have all of those bonds engaged. And it creates this, the hexagonal snowflake shape that we see when it snows. The hexagon formed by the water molecule is built upon by further water molecules, and it maintains that hexagonal symmetry. And so you can see these lovely snowflakes here. The presence of this hexagon also creates one of the anomalous properties for water. With liquid water, you can temporarily move and shift, and for a short period of time, you can actually get the molecules closer together than what you would find in this solid structure. They're not stable, but so long as they keep moving, it's fine for them to exist in an energetically unfavorable position. As we take energy out, what we find is that these hydrogen bonds start to form, and we get this hexagon starts to form. Now, the most stable arrangement for this hexagon is to basically open with a void in the middle, with a region where there's actually not that many water molecules right in the middle of the hexagon. And when that happens, it's actually pushed the actual molecules ever so slightly further apart than they could exist if it was a liquid, leading to this anomalous property where ice takes up a slightly larger volume than the same mass of water. It makes it less dense, and that leads to the unusual property of water in that its solid state has its particles further apart than its liquid state, resulting in ice floating. And we see that in everything from the ice in our drinks to icebergs. We put it all together and we find that water has these unusual properties. You see, it has both hydrogen bonding, the strongest type of permanent dipole-dipole interaction, and London forces. It means that it takes an awful lot of energy to melt it, and it means that it will also absorb a lot of heat before it does melt. And that's very important for life on Earth. The polar ice caps basically regulate the temperature. It has a large latent heat of fusion, and this is as a direct result of the hydrogen bonding that exists between one molecule and the next. But if I hadn't convinced you that hydrogen bonding was important, then let me just remind you that it is also present in DNA. Of the four nucleotides, the adenine, thymine, guanine, and cytosine, what we find is only certain combinations of bases can exist. The T and the A always connect together, the G and the C always connect together. And the reason is because of their makeup. The T and the A have molecules that will form a hydrogen bond in just the right position to form a hydrogen bond with the base on the other side. So the TA pair of bases will form a double bond, but the GC will form a triple bond. And it means that you only get T and A bonding together, and you only get G and C bonding together. And it means that we basically end up with only two combinations of nucleotide that can exist. This TA pair or a GC pair. And because it's this or that, it is essentially the binary coding of our genetic code. The sequence of these bases lead to you having the genetic characteristics of you.